As the chemist pours one fluid into another, he demonstrates one of many fluid flows that occur in countless forms throughout science and industry. The flows may be spectacular, as in this case, where the wind sets a massive structure into destructive vibration. The flow may be so common and homely an occurrence that it appears deceptively simple. It may be so magnificent that it inspires the poet, the artist, and the philosopher. To make its intricate patterns visible may require the most sophisticated of equipment. These ultra-fast movies show the delicate patterns formed during the interaction of a shock with a cylinder. It may be slow, or it may proceed with explosive rapidity. Most interesting fluid flows are extremely complicated. While it is easy to release a droplet of milk and observe its splash into a pool, it is much more difficult to measure or predict theoretically the distortion of the droplet during impact. And even though man has long been observing the crashing of ocean waves, he is still mystified by the forces that occur in the process and must design breakwaters by observation and experiment because he is unable to predict theoretically the erosive effects of the waves. To be able to make accurate predictions about fluid flows has been one of the dreams of mathematicians for centuries. In a few ideal cases, like this one, the equations of fluid dynamics can be solved easily, and the results predict the flow accurately. Almost always, however, the engineer who is developing new ideas must test them with models that are costly in both time and money. He would like to find solutions to the equations that would enable him to bypass much of the experimentation, or at least guide him to choose those experiments that are most likely to succeed. Some ambitious investigators in the 1920s discovered that with extraordinary labor, it is indeed possible to solve some of the more complicated fluid flow problems by numerical approximation techniques. One man who made a good start on a problem became discouraged, however, when he began to realize that at the rate he was going, it would take 30 more years at 8 hours a day to get the final answer. This, then, is where the recent advent of high-speed electronic computing has been able to help. Computers do no more than the man could do, but they do it incredibly faster. Here, for example, is a fluid flow, a wave released by a sluice gate. If some ambitious soul had begun working on its numerical solution a century ago, granting longevity and dedication, he would just now be finishing the job. However, one of our modern electronic computers accomplished the solution in a short period of time. Here is the solution as produced by a modern computer. What you have just seen is a typical example of a computer experiment. In a great many ways, it is similar to a laboratory experiment. A laboratory investigator requires physical apparatus to do his work. The apparatus must be set up in such a way that the boundary conditions of the problem to be solved are met. Finally, measurements are made with electronic and mechanical recorders or cameras. A computer experiment can also be described in a similar manner. The basic tool of the numerical investigator is a set of instructions called a computer program. The numerical investigator prescribes the initial conditions of the experiment, and the result of the experiment is the output of the computer in the form of printed listings or magnetic tape. In both the laboratory and the numerical experiments, there is bound to be a certain degree of inaccuracy. In laboratory experiments, errors can arise from such things as inaccuracy of instrumentation, limited lens resolution on cameras, and scaling difficulties. While in numerical experiments, inaccuracies relate to the fact that a continuous fluid can be represented by only a finite number of moving elements. These were seen in the sluice gate example as the moving dots. Here is another example of a computer experiment. We see the effect of the impact of a spherical meteor onto a sheet of metal, an important consideration in the design of space vehicles. Because of the extremely high velocity of the meteor, the materials actually flow like fluids for the fraction of the second required for the penetration. The computer enables us to see a cross-section of the collision in slow motion. Some metal is splashed upwards out of the hole, while most of the slug has penetrated completely through. Here again, we see the computer results. Calculations of this sort accurately show both the strength of the penetrating shock wave and the size of the hole that remains. Information gathered from such calculations will enable engineers to design self-sealing liners that can reduce tremendously the chances for catastrophic damage. In the design of experiments for controlled thermonuclear reactions, one goal is to compress a hot gas, called a plasma, into a very confined region. If we can get the density and temperature great enough, we can get thermonuclear power from the material. The following animation describes a plasma driven through a tube by a powerful magnetic field. When the gas reaches the end of the central cylindrical rod, it is compressed toward the axis where we hope to achieve the required temperature and density to produce thermonuclear power. Computer calculations can be made for the problem, each testing different variations in geometry, giving detailed results that cost much less than full-scale laboratory experiments. Here is an example. This is how it looks at the instant that the electrical discharge starts building up a powerful magnetic field to drive the plasma. At this point, the plasma has been driven partway up the central cylindrical rod. We can verify the calculational accuracy by comparing this configuration with a photograph of the same thing obtained from an actual laboratory experiment. The excellent agreement gives added confidence to the validity of the calculation. The fluid properties at maximum compression indicate that nuclear reactions may indeed occur with sufficient intensity to be useful. Let's watch the maximum compression sequence again. From the calculated temperature and density at maximum compression, we can determine the amount of nuclear energy developed for each case, and thus the optimum among all the variations. In a typical numerical calculation, the fluid flows through a mesh of cells that completely covers the region of interest. We invoke the basic principles of mechanics, which state that mass, momentum, and energy are conserved in any process. This means, for example, that the net amount of mass flowing in or out through the sides of a cell must be balanced exactly by the net change of mass within the cell. The same holds for momentum and energy, except that for these two quantities, the pressure forces can induce additional changes. Thus, the momentum and energy of the cell not only change from inflow and outflow, they are also affected by the net force exerted by neighboring cells. These laws of mechanics can be given precise mathematical formulation in relation to our model of fluid flow through cells. The result, then, is a set of equations describing how the fluid moves and how the state of the fluid changes with time. Even the effects of viscosity, heat conduction, chemical reactions, and various other phenomena could be included. For the computer, the changes are calculated for a sequence of steps, each generating the new results in terms of the answers from the previous step. In this calculation, we see water moving forth from a reservoir after the dam has suddenly been removed. In this example, we actually show the computational cells that were used for the calculation. In most cases, these cells are omitted from the pictures, but they are always present for the calculation. Before the computer code can be written, there are many problems to be solved in developing a computational technique that will be sufficiently accurate, stable, and general in its application. These preliminary investigations often require weeks or months of analysis and testing of ideas. Once the basic procedure has been derived, it is necessary to lay out in detail the sequence of steps that the computer must follow to arrive at the required solution. The plan is laid out on flow sheets, which show the route of the logical sequence, much as a map shows a traveler how to get to his destination. The schematic flow of steps is transcribed into a precise code of instructions that the computer can execute. The code of instructions is then punched onto cards. When all is ready, the program is given its first trial run. When the programming errors have been completely removed, useful calculational results can be obtained. Results recorded on magnetic tapes can be processed directly onto microfilm. These film records contain listings of numbers describing the fluid flow and also the computer-generated pictures. For most purposes, we need only a few selected views of the fluid configuration. But for the purpose of making computer sequences, the view is printed for every time cycle of the run. Here, the investigators are examining both the numerical and visual results on a microfilm viewer. Much analysis and comparisons with experiments and theories are required before the newly developed technique can be trusted for further explorations. The sequence you are about to see describes the splash of a droplet of one fluid into a pool of another. The study was directed towards determining the contact area between the two fluids during impact in order to predict the chemical reaction rate. This had previously never been measured or calculated. The distortions of the droplet critically affect the rate of interaction with the other fluid. Let's look at that again. Here, the crater is of maximum size, and the droplet material is spread out in a thin layer. We see the familiar splash jet that can be observed easily in a pan of water at home. The rest of the sequence shows continued undulations of the pool as the jet falls back down. When fluid rushes past an obstacle, the fluid behind may oscillate so strongly as to make an audible sound, as when you twirl a rope. This oscillating airflow behind a structure can cause it to shake so violently that it will fall apart. Because air and water are transparent, we usually miss seeing the vortices that produce these oscillations. The computer, however, can calculate this complex flow pattern. This calculation is represented in two different ways. The upper shows the streamline pattern, and the lower, the flow pattern. The obstacle is located at the extreme left of the pictures, with fluid entering the calculation region from above and below the obstacle. The sequence shows development of a double vortex pattern, the instability of this pattern, and the transition to fully developed vortex shedding. Notice again the initial tendency to form a steady flow, and the breakdown of this into the shedding vortices. The phenomenon known as Rayleigh-Taylor instability can be demonstrated by placing a heavy fluid above a lighter fluid in a gravitational field. The columns eventually develop bulges at their tips, which break off through the action of surface tension to form falling drops. The two fluids in this sequence are corn oil and silicone oil. Now we will look at the fall of a single column of heavy fluid. Notice that the amplitude of the ripple increases very slowly at first, but then more rapidly until finally a steady velocity is attained. In this computer sequence, as in the laboratory experiment, a heavy fluid is placed above a lighter one. The fluid interface is then perturbed, and the Rayleigh-Taylor spike begins to form. Notice the development of the lateral bulge at the tip. It is very similar to the development in the experimental movie. This first calculation includes the effects of surface tension. Now, the same calculation, but without any effects of surface tension. The spike grows somewhat faster now, and there is greater development of the lateral bulge at the tip. This flow is now more characteristic of gases than of liquids, due to the elimination of surface tension. In another remarkable experimental movie sequence, taken at 400,000 frames per second, we see a shock interacting with a wedge. In the laboratory, the amount of information obtainable from a particular experiment is limited. The computer experiment, however, allows the investigator to know the values of all field variables at each spatial increment. In a similar example, we see a computer calculation of a strong shock interacting with a cone. This sequence shows contour plots of the density field. The flow is now coming to a steady state, and we see its structure in detail. Again. From the computer listings of numerical results, we can calculate, for instance, the pressure on the cone, the heating of the air surrounding it, and the aerodynamic forces acting upon it. We have seen that computer studies of fluid dynamics are penetrating more and more into the complexities of fluid flow, fulfilling, to an ever-increasing extent, the needs of both the design engineer and the scientist.